This is question 3, assignment 1. This was a method that was used by Cannizzaro to get a good look at the molar mass of a gas sample, especially if you have a sample you're not sure what it is and you want to get the molar mass. So basically what you do is at different pressures, you measure the density of the gas sample, right? And this hint is kind of interesting. This is simply part of what they chose to do. This is rho, right? Pressure divided by rho versus pressure. So what you're going to find, first of all, is the ideal gas law. This is what Cannizzaro essentially was thinking about. We know that we could replace N with that. We also know that we can switch these two in place. This now is the density. So if I want to try, so I'm going to replace that with density and then bring pressure over here. So the molar mass will be density divided by pressure times RT. Now, think about this for a second though. As an algebraic thing that you're allowed to do, let's take this and put it down below, for instance. So if it's RT and you would almost have to invert, because going from here back to here, you know that you invert multiply, you'd get this. So this is equivalent to that. So pretend that this entity was something you wanted to watch experimentally. So you would have this piston, and let's just say you had this pressure gauge, and you put a gas sample in here, and you also knew, and let's say you put it on a magic, scale, in grams or whatever. So you're watching what the volume is doing for the same mass that's already in there. So I guess you don't even need the scale. As long as you have graduations for volume, you'll measure the pressure and you'll have the volume. Therefore, you'll be able to calculate the density. So think about it. What's going to happen to the density of this when you increase pressure? The density is going to go up. This formula from the ideal gas states that this denominator quantity, P divided by density, right? What do you know about as the density of the gas gets smaller and smaller and smaller? What happens to the ideal gas behavior? Any real gas, when you drop the density lower and lower and lower so it's less and less and less dense, guess what? The number of interactions is dropping. So all real gases will behave more and more ideal-like when the density drops. So what this tells me is I will get a much better molar mass when I do this example, and maybe what you could even do is put less dense and less dense. So I guess what you're going to do, think about it, you're not going to increase the pressure, you're going to back it off. So I mean, you might increase the volume to be huge so that the density of the gas is super low. So when you match the pressure divided by the density as it gets less, 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 and less, you are getting a better and better denominator thing right there to give you a more accurate molar mass. So basically what he's doing, he's not doing this to get the slope of a graph. What he's doing is, experimentally, I can only drop the density So what he's going to do is, let's say you start out at 1 atmosphere and you're saying, I want to keep having, pressure. Start at 1 atmosphere. I want to go to 0.8, I want to go to 0.001 if I could, but there's a limit to how low they could experimentally drop the pressure and still measure a density. The lower the density, the lower the pressure, the more ideal this number m will become. So I want the lowest density, lowest pressure quotient. So that's why you had P, and then this is pressure. So as the pressure experimentally keeps dropping, let's say your last data point was here, and you will see that it kind of is linear, but you experimentally couldn't get any lower than this. So what you want to do is estimate what this graph is telling you you'll end up with at 0 pressure. What value for this at 0 pressure will I get? So you'll graph this with the data he had, you'll extrapolate it, and guess what that y-axis value would be. Once you have that from a straight line pretty much equation, you'll take that y-intercept, put it in place of that, calculate your m. That's what you're doing. That's the method. In the ballpark answer, if you do it this way, you're not getting a slope of a line. You're getting a y-intercept in the limit of 0 pressure. So the range